Okay, everyone concentrate here. Next one is in direct loading method, we have seen how to calculate efficiency, output power by input power into 100% efficiency. Okay. Now, another formula also we'll see. All of you know efficiency is output by input. So input, all of you know efficiency is not 100%. Whatever the input you give to any system, some losses takes place in it and the rest is converted into the output. Okay. So input I can say is equals to output plus losses. And we have seen the losses in transformer, iron loss and copper loss. Okay. So this is the modified formula for efficiency. Now output power is single phase. This is the single phase transformer. So output power is single phase AC power. Formula is V2I2 cos of phi, where cos phi is a load power factor, the load which is connected across secondary. Now this is the output divided by output plus iron loss plus copper loss. Okay. Now this is the general formula of efficiency. Now here copper loss, we have seen it, copper loss I1 square R1 plus I2 square R2 referred to primary, referred to secondary. All this formula keep in your mind. Okay. Because while solving numericals, either this one or this one or this one you have to use. Okay. So this is the copper loss. Using this formula you can calculate the copper loss. Now this one, all of you know kVA rating. We have seen kVA rating into 10 to the power 3 is equals to V1 I1 is equals to V2 I2. So whatever this V2 I2 in this formula, I can replace it by kVA rating. So see, it's a simplified form. V2 I2, if you replace by kVA rating, what it will be? kVA rating into 10 to the power 3 cos phi divided by same parameter. Because if you see this numerator and in the denominator, whatever is the first parameter is same. Okay. So that's why this one and this one will be same. Okay. So kVA rating into 10 to the power 3 cos phi, same parameter here, plus iron loss plus copper loss into 100%. Okay. Now, whenever I say here kVA rating, so on the nameplate, you find only full load kVA rating. When the load is half, then kVA rating becomes half. Okay. But that is easy. Suppose it's a 100 kVA transformer. If you get asked calculate the efficiency, directly you can put here kVA rating as 100 because that is the kVA rating at full load. Whatever given on nameplate. Also, if on the nameplate mention 100 kVA rating transformer, that is the full load kVA rating is 100 kVA, it does mean, and you get asked calculate the efficiency at half load, then whatever the kVA rating at full load, half of it is the kVA rating at half load. Means if full load kVA rating is 100 kVA, then half load kVA rating is 50 kVA. So that also, and one more thing is there, whatever the, then what's about the copper loss? Whatever the copper loss takes place at full load, kVA rating you can make half. If the load becomes half, then kVA rating also becomes half. But what's about copper loss? 1/4. Suppose full load copper loss is 1200 watt. Then how much it will be at half load? I told you 1/4 of it. Means how much it will be? 1/4 of 1200. Means how much is 1/4 of 1200? 300 watt. Got it? 300 watt. Okay. So this one relationship, everyone please keep in your mind. That is whatever the copper losses takes place at full load, 1/4 of it occurs at half load. You can write down the formula 1/4 of full load copper loss is equals to half load copper loss because it's a I square is there. That's why. That derivation you can see in BL Thareja, that is not included in your syllabus, directly the formula. Okay. But this is about the half load condition. But sometimes you may get asked calculate the efficiency when the load is 75% of full load, 85% of full load, 80%, 40%, 60%. Then in that case, what will be the kVA rating? What will be the copper loss? So in such condition, one modified formula, which one you can use in general for all type of load. For full load also, half load also, 75%, 80%, 85, 60, 40, whatever is the load on transformer, only one formula of efficiency, all of you keep in your mind this one. Okay, very important it is. That is percentage efficiency, and where this small n is what, see here, n is there, and here n square is there. So what is the, here n stands for? It's a ratio of actual load upon full load. Suppose it is given to you, calculate efficiency at full load. Full load means how much load is there on transformer? Fully loaded means actual load value is here, full load will be there upon full load. So full load upon full load, so it will cancel. So n will be 1. Means whenever it is a full load, a value of n is 1. Here also 1 square. If it is a half load, then what? Actual load is half of full load. Suppose you get asked calculate this efficiency at half load. So actual load is what? Half of full load. So half of full load upon full load will cancel. N is equals to half, that is 0.5. So whatever this formula of efficiency you can use to calculate any efficiency at any load. So half for half load, value of n will be here 0.5 and here 0.5 square. What does it mean when the load, if I am using here n as 0.5, n as 0.5 here and here 0.5 its square, what does it mean? For that half load, in the numerator you will get the kVA rating at half load. Here also you will get the kVA rating at half load, because when load becomes half, kVA rating also will become half. And what's about copper losses? See, 0.5 means 1/2. 1/2 its square means what? 1/4. Means 1/4 of full load copper loss is the copper loss which takes place at half load. Means what is the advantage of using this formula? Directly using this, you can calculate the value of n, and then suppose 80%. 80% of the full load is there on transformer, and calculate the efficiency. Then it will be how much? 80% of full load means 0.8. Means 0.8 into kVA rating will be the kVA rating at 80% of full 80% of load, and 0.8 square into full load copper loss will be the actual copper loss which takes place when load on transformer is 80% of that full load. Means directly here you will get the copper loss at that particular load. How? By using n square full load, n square times full load copper loss, and by using n into kVA rating into 10 to the power 3, you will get for that particular load what is the kVA rating. Okay, so this is the benefit. So only one formula for efficiency. All of you please keep in your mind. On this, numericals are included in your syllabus. Okay. Now this one I think I told you. This point is explained now why efficiency initially increases, decreases, and reaches to maximum, because at maximum efficiency iron loss and copper loss are equal. Below maximum efficiency point iron loss is greater, and after efficiency point copper loss is greater. I think this one point in previous lecture I have covered. If not, please tell me, I will repeat. Okay, I think it is covered. Then next, now see here. This is the efficiency curve we have seen in previous lecture, efficiency versus output power. Now here output power is increasing, means nothing but load you on transformer you are increasing, current increases. Okay, so at this is the maximum efficiency point. Sometimes in numerical you get asked calculate the maximum efficiency of a transformer. Then there you have to use this relationship. Its derivation not there in your syllabus. Those who are interested can see the BL Tharija. Okay, iron loss and copper loss both becomes equal at maximum efficiency point. Now at this maximum efficiency point, sometimes you get asked calculate the current. Sometimes you get asked calculate the kVA rating at this maximum efficiency point. So again, for current at maximum efficiency, for kVA rating at maximum efficiency, derivation not there in your syllabus, directly the formula. Those who are interested can refer BL Tharija. Directly formula you keep in your mind that at maximum efficiency point, whatever the current flowing is, how much it is, that is marked as I2M, means current on secondary and at maximum efficiency. Output current, it is load current. M stands for maximum efficiency. How much it is? So secondary winding full load current into square root of iron loss upon full load copper loss. Here all of you keep in your mind, here it's a full load copper loss. In this formula also, here see, here full load copper loss is there specifically. Now load KVA rating, KVA rating at maximum efficiency. So what is the formula? Full load KVA rating into square root of iron loss upon full load copper loss. Here I have not used for KVA rating suffix full load. By default, whatever given in the specification is always full load KVA rating, unless and until they don't mention anything. If they mention the single phase 50 Hertz transformer of 100 KVA rating, means what does it mean? It's a, by default, it's a full load KVA rating. Okay. So this is nothing but full load KVA rating you have to use here, or you can use here suffix also, or full load. Okay. So full load KVA rating into square root of iron loss upon full load copper loss. So just put the value in the formula and you will get at maximum efficiency point what is the current and what is the KVA rating. Okay. Sometimes they ask you to calculate in the numerical, you get asked to calculate the efficiency at calculate the maximum efficiency of a transformer, and there you load is not mentioned. So you cannot calculate the N, value of N. So that time, to calculate the KVA rating at maximum efficiency, this formula helps to do. Okay. So KVA rating at maximum efficiency, you can calculate using this formula. Okay. Based on this formula, now we'll see the numericals. Again, I am repeating. See here. This is the important formula. This one formula you have to use. Secondly, sometimes they are also required to calculate the copper loss also. Second one. Okay. Third one, condition at maximum efficiency. Fourth one, current at maximum efficiency. And fifth one, KVA rating at maximum efficiency. Got it, everyone? Okay. So whatever the sum you will get asked on efficiency, these formulas you have to use. We'll see the sum. A transformer is rated at 100 kVA at 100 kVA at full load. Its copper loss is 1200 watt. Full load copper loss is given 1200 watt. KVA rating is 100 kVA, which is at full load by default. And iron loss is 960 watt. This iron loss is constant or variable? Constant. We have seen iron loss is constant. So for whatever is the load, iron loss value always please take 960 watt. But what's about copper loss? Only full load copper loss is given to you 1200 watt. Full load KVA rating given to you 100 kVA. As load changes, KVA rating changes. As load changes, copper loss changes. Okay. But iron loss constant. See next. You have been asked to calculate the efficiency at full load efficiency. And what is the load power factor? That is also given. How much? Unity power factor. Means it's a power factor of the load which is connected across secondary. So easy. Efficiency formula you know. See. So you have been asked to calculate the efficiency at full load. So what is the value of N here? N means what? Actual load upon full load. So full load upon full load means what is the value of N? What will be N? 1. Okay. In this formula, you have to put 1. Here KVA rating is full load KVA. In this formula, whatever I have written N is actual load upon full load. Whatever I have written KVA rating, nothing but it's a full load KVA rating. Okay. So full load KVA rating is given 100 KVA. Means that value also we got, N we got, KVA rating we got, 10 to the power 3. Then what else? Cos phi. Cos phi also given, see. N we got here, KVA rating is given, here N square also we got, cos phi is given 0.8. So all these values we got, see cos phi is given, sorry, 0.8 not 0.8, unity power factor. For full load, it's given unity power factor. For half load ke liye 0.8 दिया है. ठीक है. So for full load, unity power factor means cos phi value is 1. Again, what else? Iron loss also given to you 960 watt. Means that this value also we got 960. And what is this? Full load copper loss. And full load copper loss is also given. How much? 1200 watt, means all value now you have. N is 1. Just now we have seen, see, N is equals to 1 and all values are given. Put the values, efficiency into 100 will be the percentage efficiency, 97.88. Any difficulty with this? Very easy sum. Okay, no difficulty. Fine. Now see next one. What is it? Calculate efficiency at half load, 0.8 power factor. So what will be the difference compared to previous one? KVA rating value will be same. 100, 100 here. Here iron loss 960 and full load copper loss 1200. Isn't it? All these values will be same. Now half load. So what will be the value of N? N is actual load upon full load. Actual load is half load. So half load upon full load. And half load is what? Half of full load upon full load. So what value of N you will get? Half, that is 0.5. So put here 0.5, 100 kVA, 0.8 given power factor. Whatever is this parameter, same here. That's why I have written numerator, but you don't write so. You have to write complete parameter. Plus iron loss given, plus N square, that is 0.5 square full load copper loss into 100, 96.95. Only in formula you have to put the value. Any difficulty with this? Next one. Next one. Okay, next one, see. Calculate the efficiency at 75% of full load when the power factor is 0.7. So 75% of full load. So see here. This one. See, 75% of full load. So actual load upon full load. Load is how much? 75% upon full load upon full load. Full load will cancel and you will get 0.75. Okay. So put the value. See here. 0.75 into 100 into 10 to the power 3. Power factor is given 0.7. Divided by same parameter plus iron loss 960 given plus N square we have calculated 0.75 into full load copper loss. So 96.98%. Okay, so easy. I think everyone can calculate. Next one, you have been asked next. So efficiency at any load, now all of you can calculate using this formula. Okay, only in formula you have to put the value. This part is done. Fourth one, see. Load KVA at which maximum efficiency will occur. Means load KVA, find out the load KVA at maximum efficiency. I told you the formula already for that. What is the formula? KVA rating at maximum efficiency. Full load KVA rating into square root of iron loss upon full load copper loss. All values given already in the numerical. Right? KVA rating 100. I want answer in KVA. That's why this KVA rating I am going to put as KVA only, not into 10 to the power 3 I am doing, because answer I want only in KVA. That's why. Okay. If options given to you are in volt amperes, then you have to do here 100 into 10 to the power 3. But I want answer in KVA. That's why I put it as 100. 100 KVA into iron loss given 960, full load copper loss also given 1200 watt. And 89.44. Okay, only in formula you have to put the value. Last one is very important. All of you concentrate here. Last one parameter is very important. See, maximum efficiency at 0.85 power factor. Up till now, whatever the efficiency you get asked to calculate, if you observe here half load given, full load given, 75% of full load given, means value of N you can calculate. N is actual load upon full load. Using that value of N you can calculate. But here you can't calculate N. See, you have been asked to calculate the maximum efficiency and load power factor is given 0.8, but how much is the load? That is not mentioned. Maximum efficiency can occur at half load also, full load also, or it can happen. It can occur at 75% of load, 80%. That is not given. If load is not given, then you cannot calculate N, isn't it? So what you can do here? See, formula we know. Formula of efficiency we know. So whatever the load KVA rating just now we have calculated, that is nothing but this one. See, this complete parameter is nothing but whatever you have calculated right now, load kVA rating at maximum efficiency. Means this 89.44 is nothing but which value? N kVA rating. Got it, everyone? Maximum efficiency N kVA rating, nothing but this is how much? 89.44. Okay, put it here. Power factor is given to you 0.85, 0.85, 960. And I told you that at maximum efficiency, what is the condition? Iron loss is equals to copper loss. Means that N square full load copper loss value, how much you will take? N square full load copper loss value, how much you will take? Same as that of iron loss, because maximum efficiency we are calculating here. We have seen the condition at maximum efficiency, iron loss and copper loss are equal. Everyone got this point? Any difficulty with this? See, this is the load kVA at maximum efficiency, and efficiency here you have been asked to calculate maximum efficiency. So N kVA value you have to put here 89.44. This is the first thing. Second thing, N square full load copper loss. Value of N right now we don't know. But condition at maximum efficiency we know that when iron loss, if iron loss is 960, then copper loss also you have to take 960. That's why N square full load copper loss 960 here. So whatever the efficiency you will get, that will be maximum. Is this clear to everyone?
Yes, ma'am.
Can anyone tell me? Can anyone tell me whatever the part we have covered now, we can calculate the value of N at maximum efficiency. How to calculate? Can anyone tell me? I can calculate N also at maximum efficiency. Two options are there to calculate the N. Up till now, actual load upon full load दिया रहता है आपको 75% full load, half load, so easily. But here load is not mentioned, but still I can calculate the value of N. Can anyone tell me how you can? See, this is the kVA rating at what? Maximum efficiency. If I equate it to N into 100 kVA, can I equate it to N into 100 kVA? Then whatever is the value of N will be what? N at maximum kVA, M at maximum, N at maximum efficiency, isn't it? Equate it to N into 100. Isn't it? Yes, students? N into 100 equal to this. If you do N at maximum efficiency, you will get. You try this. Whatever you got this value, na, put here, see 89.44 is equals to N into 100. Means N, how much you will get? 0.8944. So put here 0.8944, and N square also 0.8944 into 1200 you put here, and here you put 100. Same answer you will get, 97.54. Or what is the another option to calculate the N? See here, condition at maximum efficiency we know. What is it? N square full load copper loss is equals to 960. Iron loss is equals to copper loss at maximum efficiency. Equate it. See, same value of N you got. Now, two options are there to calculate the N at maximum efficiency. N square full load copper loss. Here full load copper loss put 1200 and equate it to 960. Whatever the N, that will be at maximum efficiency. This is the one option. Second option to calculate N, equate it equal to N into 100. Then also you will get the N. And then whatever this N you got, put it here. 0.8944, 0.8944, and here N square means 0.8944, its square into 1200 will be 960. See here I have written already. N square into full load copper loss is 960. Means ये automatically 960 ही आता है. ये देखो यहाँ पे लिखा है मैंने. ये देखो N we have calculated 0.8944. ठीक है. So ये देखो N into full load kVA rating. ये 0.85 already given. Numerator will be as it is. 960 iron loss. See, N square 0.8944 its square into full load copper loss. Same answer. 97.54. Here also see 97.54. Any method you can use, or I have written here. Got the sum on transformer? Is this clear to everyone? Any difficulty with this? Yes, any difficulty?
No, ma'am.
Okay.
No, ma'am.
Okay, we'll start with now unit 4. AC circuits. One PDF I open.
मॅम तुम्ही एकदा ते युनिट 3 चे आणि युनिट 4 चे हँड रिटन नोट्स सेंड करू शकता का परत व्हॉट्सअपवर?
Are you there on Google Classroom?
येस मॅम.
So on Google Classroom everything is available.
Okay.
Please check. Whatever I posted on WhatsApp now, everything is available on Google Classroom also and VOLP also. Okay, everything I loaded. Lecture links, all these handwritten notes. Again, that whatever the extra material I forwarded to you, everything. Okay. So see here, unit 4. Unit 4, 3-phase AC circuit. 1 minute. Okay. Start करते हैं now. 3-phase AC circuit. Okay. One more required for this that I open it. Just a minute. Okay. Okay. Fourth one unit, 3-phase AC circuit. Now here see, in second unit we have seen about single phase AC supply. Okay, single phase AC supply. This is the north pole, this is south pole. From north to south pole, magnetic field will flow. Now this is the direction given of magnetic field between north and south pole, denoted by this dotted line. Now in this magnetic field is stationary. You rotate this one coil continuously, like this one coil. Now, as per Faraday's law of electromagnetic induction, whenever there is a relative motion between field and conductor, EMF get induced in the conductor, and whatever EMF get induced in this conductor, we have seen in second unit, whenever this coil, it's plane, and this magnetic field, both are parallel to each other, will be at 0 degree, isn't it? Then no d phi by dt will be there. EMF induced in the coil will be 0. And as you rotate that coil through 10 degree, 20, 30, 40, 60, so on, so d phi by dt will be there. And at 90 degree, maximum d phi by dt will be there. So maximum EMF get induced in it. Okay, and so on. This one number of times we have seen this coil as you rotate from 0 degree up to 360 degree. So this is the nature of EMF induced in that coil. Okay, and continuously, this is the one revolution. Continuously you go on rotating it. So like this will be the nature of EMF induced in this coil. This is the graphical representation. And what is mathematical representation? V of t, Vm sin of omega t. In its Phasor diagram representation also we have seen along positive real axis, magnitude is equals to RMS value, right? So graphical, mathematical, and Phasor diagram. This is about the single phase AC supply. Here you have placed one coil. That's why you are getting single phase AC supply, single phase AC voltage. This is the principle which is used in generator. Generator, all of you may know, input we give mechanical and output is electrical. You are rotating this coil, nothing but you are giving mechanical input. And EMF get induced in it, nothing but it's a electrical output. So this principle is used in generator. This is nothing but you can say it's a small generator. Okay, got it? So what's about 3-phase? Here single coil is there. Now like this, you can use 3 coils. See, between north and south pole, you can find 3 coils are there on rotor. In generator में क्या रहता है? In generator, if you see, whatever this north and south, it is nothing but it is mount on stationary stator. That portion where these north and south poles are wound, that is called as stator, and where these 3 coils are wound, that is called as rotor. Stator and rotor both are circular cylindrical, and on this stator these poles are fixed. On the rotor these 3 windings are wound. We give mechanical input to generator. Because of that, these 3 windings starts to rotate, and then they are cut by this flux. So what will happen as per Faraday's law of electromagnetic induction? EMF will get induced in R phase winding also, Y phase winding also, and B phase winding also. 3 windings are there. First one is R phase, second one is Y phase, that is called, and third one is called as B phase winding. Now what is done while designing? While designing generator, they place these windings all over the rotor. In rotor slots are there, and in the slots they put these windings. Now these windings are so placed that whatever the nature of EMF induced, whatever the nature of EMF induced in that 3 windings, it will be like this. See, these are the instantaneous equation. Means whenever you are rotating, you are giving mechanical input to rotor. These 3 coils you are rotating continuously. They get cut by this flux. Then as per Faraday's law of electromagnetic induction, EMF will get induced in this winding. Now whatever the EMF get induced in this windings, what will be their mathematical expression? See, in R phase winding and Y phase winding and B phase winding are designed on rotor so that whatever the EMF get induced in R phase winding, that will always be EM sin of omega t. EMF induced in Y phase winding, its behavior will be EM sin of omega t minus 120 degree, and EMF induced in third coil, see here RYB, 3 coils are there. So whatever the EMF get induced in B phase winding, its instantaneous voltage equation is EM sin of omega t minus 240 degree. Designing is a different part that is included for electrical students. Okay, generator, motor, winding design, transformer also. So they design the windings so that Y phase voltage. Now if you observe this 3 instantaneous equation, if in some books you will find here, see instantaneous value. We have seen in AC fundamental, instantaneous value are denoted by small letters. See here, small e, and they are not constant. They are the function of time. As time changes, its value changes, and that is the instantaneous. In some books, you will find suffix use is ER, EY, and EV. In some books, suffix used is VR, VY, and VB, small v. Because instantaneous value. Any of it you can use. If you are using small e, then use here capital EM, peak value. All of you know peak value we always denote by capital letter suffix M, here EM, here EM, okay? But if you are using small v here, small v here, then here please use capital V suffix M, capital V suffix M, capital V suffix M, okay? Got the thing? So in some books you will find small e, in some books you will find small v. So if you observe this 3 instantaneous voltage equation, you can find peak of each is same, EM, peak is same. All 3 waveforms are purely sinusoidal. See, for all 3 purely sinusoidal AC, all 3 waveforms, their angular frequency is also same. And that's why whatever this 3-phase AC supply, it is called as symmetric 3-phase AC supply. Definition, what do you mean by symmetric 3-phase AC supply? So, symmetric 3-phase AC supply means their peak is same, their nature also same. See, all 3 are purely sinusoidal AC, and their angular frequency is also same, which is omega. Now, only the thing is that all windings you cannot put only at one place. You have to distribute it all over the rotor. That's why there is a phase difference. So you will find whatever the EMF get induced in Y phase, minus sign is there. Means it lags or leads?
Lags.
Lags. By how much degree?
120.
120 degree. And it lags by 120 degree to which phasor?
Yeah.
R phase voltage. Correct. ER. Correct. Similarly for Y phase, you can similarly for B phase, you can see it lags by 240 degree to R phase voltage. Like this windings are designed. Or in another word, I can say this B phase voltage, it lags to Y phase by how much degree?
120.
120 degree. Correct. Okay. So this is the mathematical representation of the induced EMF in that 3 coils. Okay. Again, its graphical representation will be like this. See, this is the single phase AC voltage. Number of times we have seen V of t, Vm sin of omega t. Okay. Or I of t, Im sin of omega t. Same nature. Whatever the 3 phase AC supply. See, first one equation. Vm sin of omega t Vr, which is red color waveform. See, that one we know its peak, first positive peak occur at 90 degree, isn't it? That waveform we know. Then second one equation is what? Vy is equals to Vm sin of omega t minus 120 degree. So all of you can see this yellow color waveform from 120 degree, it starts increasing positively. Isn't it? Whenever I say there is a phase difference between R and Y is 120 degree. So all of you in second unit also I told you in AC fundamentals, whenever I say the phase difference between the two waveforms is 120 degree. So same is the phase difference between their first positive peak. So all of you can see here, first positive peak of R phase is occurring as 90 degree. So 90 plus 120 degree means how much it will be? 210. So at 210 degree, Y phase peak will occur, first positive peak. Isn't it? Got everything? And see the third one, Vm sin of omega t minus 240 degree blue color waveform. So here also phase difference between Y and B 120 degrees. So their phase difference between their first positive peak also 120 degree. Everyone got the graphical representation? Okay. So this is the graphical representation, means this is the actually AC generator, its output. In India, electricity is generated using generator, and that generator is 3-phase AC. Like this means windings, that 3-phase windings they put on rotor and stationary stator poles are there. Okay. So this is the arrangement, and whatever the 3-phase induced EMF in these 3 windings, that is Vm sin of omega t, Vm sin of omega t minus 120 degree, minus 240 degree, that is the output, electrical. Input is mechanical. Okay. This is the case for smaller size generator. For larger size generator, what is done? Reverse is the case. Reverse is the case means what? These 3 windings you will find on stationary stator, and that poles is there on rotor. Okay, because you have to start in larger generator, induced voltage is very high, so that higher voltage you cannot keep rotating, that will be risky. Okay, again many disadvantage it has. Better it will be if you make it stationary. That's why reverse arrangement. Okay, so this is just for your information. It's not included about generator or anything, but just in 5 minutes we'll tell you what do you exactly mean by 3-phase AC supply and single phase AC supply. Okay, so see, just now I told you generating station, you consider this one where generator is a major equipment which is used for the generation of electricity. Okay, so in India, electricity is generated in the form of 3-phase AC, 50 hertz supply. Okay, so on this generator, larger size it is. So larger size means that 3 winding you will find on its stationary stator, and they are star connected like this. Star connection also today we are going to see star connection like this. This is the R phase winding, Y phase winding, and B phase winding. And then the terminals they brought outside like this. Like this. So this is R, Y, B. So you may have heard that is the 3-phase AC supply RYB. This is nothing but what is done. Whatever the stator here on generator, 3 windings are there. They are connected in star like this. See, star connection like this. R phase winding of generator, Y phase winding of generator, and B phase winding of generator. And then इसमें EMF induce होता है. EM sin of omega t, EM sin of omega t minus 120 degree, EM sin of omega t minus 240 degree. And these terminals they brought outside. R, Y, B. Neutral also you can tap. Whatever this common point of 3 windings, tap here from 1 wire, and that is called as neutral wire. Okay, clear? Star connection. Huh? So like this connections of windings you will find here on stator. And then from here they tap 3 terminals, RYB and neutral. So consider this generator is generating voltage, generating electricity in the 3-phase form. What I am telling to you, what do you exactly mean by 3-phase and single-phase AC supply? Okay, so just listen it. So it will be clear to you. So consider this generator, it generates the electricity at 33 kV. Now, if you transmit the electricity at 33 kV, whatever the transmission losses, I square R loss, because the generating station is not nearby your home, it is far away. Means this electricity needs to transfer over very large distance. So whatever the transmission losses, I square R, you can minimize. How? Step up this voltage rather than transmitting electricity at 33 kV, step it up. So that's why this is called as substation. This one is generating station. Where generator is the important machine. Substation, where transformer is the important equipment, major equipment. So substation you will find. Then what is done there? Using transformer, they step up electricity. Transformer, just now we have seen to step up or step down the voltage. So see here, application of transformer, they step up the voltage 220 kV. We have seen voltage, if you step up on secondary, current will be less compared to primary, and that's why I square R loss over transmission losses over larger distance will be less, isn't it? Then we don't want 220 kV. We want only 220 volt single phase and 420 volt 3-phase. So there is a need to step it down. This 220 kV, once you transmit over larger distance, very large distance, this get transmitted. Then there is a need to step it down. So again, step down transformer. Again, this is the substation. So it step it down to 11 kV. Further, we don't want 11 kV. Further, it is stepped down to, see, this is the transformer. Just in continuation, primary, I have shown on your right and secondary on left. Otherwise, in this previous to reverse the case. So see, this transformer you will find at the back side of our workshop also. Distribution transformer in college. Here only for that transformer, here 22 kV is there. In electricity reaches up to that transformer at 22 kV. Here I have considered 11 kV. Okay, whatever is the voltage, 11 or 22. So everything is in the form of 3-phase. Up to this point, everything is in the form of 3-phase AC and 50 Hertz. Okay, so 3-phase transformers are all these. Means 3 windings there on primary, connected in either star or delta, and 3 windings there on secondary. So whatever this distribution transformer, back side of workshop, nearby also you can find the distribution transformer. So this distribution transformer, you will find whatever the 3 windings there on its secondary, they are always star connected. See, like this. Just now I have shown you star connection for generator. Same star connection is used for distribution transformer its secondary also. Now what is done? Whatever these 3 windings there on its secondary, they are connected in star. In star means this is the R phase, Y phase and B phase winding. See, one common terminal. Why they are connected in star? Because neutral point is available only in star. From this common point, they tap one wire and that is called as neutral. And this is neutral means nothing but it's a wire which with black color insulation. All of you know at your home socket, one terminal is phase, another one is neutral. So that live phase is any of this. Either it can be R phase or Y phase or B phase. But what's about that second one, neutral, black color insulation? It is nothing but it is the one which is tapped from the transformer. It's a secondary winding star connection from the star point. Okay, that is the connection tapped from it. Now, why it is required, this neutral connection will tell you. So see here, this is the transformer secondary. It is star connected. Just now in this unit we'll derive the derivation for star. Now here see, on secondary winding is star connected and neutral wire is also there. Means 4 terminals are available. RYB 3-phase AC supply terminal and neutral wire also. Now this is called as 3-phase 4-wire AC supply. So what is done, from every distribution transformer, number of cables they tap. And that cable, if cut section, if you see, it has 4 core. One is R, another is Y, next is B, and last one is neutral. So like this, cable is tapped from transformer, and that is given in our college to all building. One cable to A building, B, C, D, E, like this. Okay, workshop, marine. So to every building at your home also, means whatever is your building, up to that building, from this transformer, its secondary star connected, and cable is tapped from here RYB neutral. So like this cable reaches to each and every building. Now, what is done? See here, voltage 11 kV to 420. Whenever I say secondary side voltage is 420 volt, what does it mean? If you measure voltage across RY, YB and BR, that is called as line voltage. That will be 420. So 3-phase 4-wire AC supply 420 volt 50 hertz. And these AC supply we are going to give in this unit to 3-phase AC load, and such circuits we are going to simplify. Okay, so this is about the 3-phase AC supply. And what's about single phase? Now once this reaches at your home, this at your building, R, Y, B and neutral, like this, 4 wires are there. So what is done? Suppose it is reaching in our college to E building, first year building. So what is done? Some load of that building, E building, they put on R2 neutral. Single phase AC supply 220 volt, because this is the star connection, and we will derive in this unit voltage across RY, YB and BR. Just now I told you 420 volt. So for such connection, when you tap this neutral, so whatever the voltage across R2 neutral, Y2 neutral and B2 neutral, that is 420 divided by √3, and single phase AC voltage 220 to 240 volt. So 3-phase AC voltage, if you want, RYB neutral you use, 3-phase 4-wire AC voltage supply. That is R2Y, Y2B, B2R, 420 volt you will get. If you want single phase AC voltage, what is done? Some load of one building they put across R2 neutral, 240 volt, 220 volt single phase AC supply. Some load of that building they put across Y2 neutral and some across B2 neutral. So what do you mean by 3-phase and what do you mean by single phase AC supply? Clear? Okay, so like this is the system practically. Generator, then step up transformer, step down transformer. This is distribution transformer. MCQ question. Secondary winding of distribution transformer is always, how it is connected, in star or in delta? MCQ question.
Star.
In star. Keep this in your mind. Okay, it is always connected in star. Okay, so this is the 3-phase AC supply, and R2 neutral, Y2 neutral, B2 neutral, single phase AC supply. Okay, so single phase AC supply we have done in second unit. Now 3-phase AC supply. Okay, so whatever the 3-phase AC supply, its R phase voltage equation is this one, Y phase and B phase. Graphical representation also we have seen. Now what's about its Phasor diagram representation? Now all of you know Phasor diagram. See, alternating quantity, magnitude and direction. So you can represent them in the form of Phasor diagram. So this will be first one. Phasor will be along which axis? Em sin of omega t. It will be along which axis?
X-axis.
Positive real axis, that is the x-axis ER, and its magnitude will be equal to how much? Peak value or instantaneous or RMS or average?
Peak value.
RMS value. In Phasor diagram, whatever is the magnitude is equals to RMS value. Okay, RMS value. Now, if peak of all these 3 waveform is same, then what's about their RMS value? Also will be same. Okay, so all of you can see here ER, EY and EB, their magnitude is same. So ER, EY lags ER by 120 degree. Lagging parameter we always measure in clockwise direction. That's why EY lagging to ER by 120 degree and EB lags ER by 240 degree. Lagging parameter we measure in clockwise direction. That's why EB lagging to ER by 240 degree. So ER along positive real axis, EY in third quadrant and EB in second quadrant. Got it, everyone? Any difficulty? with phasor diagram representation. Okay. So this
No,
is
ma'am.
about this is about the three-phase AC supply. Now what we are going to see in this unit, whenever this three-phase AC supply you apply across star connected load and delta connected load, what will be the power, what will be the current relationship, voltage relationship, phasor diagram and numericals on this. Okay, that will be done in next lecture, means tomorrow. And next to that on Saturday, last part, work power energy. Okay, so can I end meeting because you are having next lecture, no?